Morning, and welcome to Accelerating Big Data Analytics Applications with FPGAs and OpenCAPI. My name is Peter Hofstee. I work at IBM in Austin, Texas, and part-time at Delft Technical University in the Netherlands. So just as a reminder, in this first module, we're providing some background and motivation, crash course in the relevant computer architecture, if you wish. In this sub-module, we'll look deeper into why you might want to use accelerators. So specifically, we'll look at the question of why can't we just use faster CPUs or use more of them? What are the limits to homogeneous multi-core processing? And exactly how do accelerators help? So while in the first module we took a little bit more of a software view of things, here we are taking more of a technology-focused view of scaling limits, latency, and throughput. So in turn, we'll go into the technology aspects of making a CPU faster. We'll discuss the limits of multi-core processing from a technology perspective, and then talk a bit about heterogeneous architectures and special purpose systems, and briefly touch on reconfigurable computing. So what are some of the specific ways in which we might make computers faster? One of them, of course, is to use faster technology, faster transistors. Another is better circuit design. We can use more transistors and improve the microarchitecture to make a computer go faster. We can use concurrency, and we can use specialization. For the first 35 years or so, microprocessors became faster by following something called Dennard scaling. So what Dennard scaling says is that if you take a transistor and you reduce all dimensions by the same factor, X, Y, and Z, and you reduce the voltage by that same factor, then your transistor density obviously increases by the square of that factor for planar designs, and your power density remains constant. And this is because capacitance and frequency both increase linearly, and voltage decreases linearly, but the formula is CV squared F for the power to first order. So CV squared F would remain constant. With the end of the Dennard scaling, as the oxides became too thin and current started leaking from the controlling gate to the channel of the transistor, further scaling required materials such as high-K dielectrics, and structure changes such as FinFETs and soon gate-all-around transistors. And since the end of the Dennard scaling around 2005 or 65 nanometer, frequencies have not improved much. Now, complementing Dennard scaling, which tells us how a design migrates from one technology to the next and improves, we have Moore's law, which tells us that the number of transistors per chip grows exponentially over time. The constant has varied from 1 to 3 years, but remarkably, even now, this law, which is really more of an observation or a rule or perhaps a self-fulfilling prophecy, is still very much in effect, and transistor densities do continue to improve. So microprocessors not only improve from improved technology, they also improve from improved microarchitecture. And perhaps the best example, and one of the earlier ones of improved microarchitecture, is pipelining. Early microprocessors handled instructions one at a time, and with the introduction of pipelining, an instruction would go through its different phases, like instruction fetch, decode, execution, with an instruction in each of the pipeline stages in parallel. This improved actually both the performance and efficiency, one of the few times when a microarchitectural improvement was able to do both at the same time. However, micropipelining also has diminishing returns. A cycle boundary latch introduces a certain amount of delay, and in the limit, that delay places a limit on the frequency that could ultimately be achieved, even if other aspects, like the amount of power that you dissipate, don't limit you sooner. So while pipelining, as well as improved transistor performance, vastly increased the frequency of microprocessors, the speed of memory, in particular DRAM memory, has not improved nearly as fast. And that meant that memory is effectively further and further away, measured in processor cycles. And a lot of the additional transistors that became available had to be used to compensate for that memory going further and further away. Of course, the most obvious use there is of those extra transistors is to introduce caches on the microprocessors that keep at least the often used data fewer cycles away from the core. On the instruction side, we have branch prediction, so we can fetch the instructions prior to when they are needed and cover some of the latencies that way. And also out of order processing, which is typically accompanied by forms of speculation, again, to help cover the fact that memory is further away and also create a higher degree of concurrency within the core. So all of these have been architectural means that leverage the additional transistors available to us. Now, in the previous submodule, we already mentioned Pollak's rule. Just to remind you, it says that for many things that we do with microarchitecture to make processors more powerful, the return is the square root of the investment in the number of transistors, i.e., make something twice as good for 4 times as many transistors. So in this slide, you can see what happened to microprocessors between the early days in 1971 and 2000. So the frequency improved by about 3 orders of magnitude. The number of instructions per cycle improved by also almost an order of magnitude. And the number of transistors grew by 4 orders of magnitude over this period. The performance, however, improved only by 4 orders of magnitude. In other words, if you might have hoped that your performance might have doubled with both a doubling of the number of transistors and a doubling of the frequency, that is actually not the case. The additional transistors were needed to compensate for the negative effects of the increased frequency. And when the number of transistors multiplied by the frequency grew by a factor of 10 million, the performance grew by a factor of 10,000. So as a consequence of the end of Dennard scaling around 2005 and diminishing returns on microarchitectural mechanisms such as deeper pipelines, around 2005, frequencies saturated, and as a result, microprocessor performance no longer improved at an exponential rate. Note that the scale on the left is the logarithm of performance. And therefore, the community had to look for a different means of increasing performance of computers. When frequency no longer was available to us to increase processor performance, we turn to a more efficient means of increasing microprocessor performance, i.e. concurrency, and processors instantiated multiple cores and multiple threads. You know, the good thing is here that the performance goes up linearly, at least for those problems that are parallel. But there are challenges as well, like memory bandwidth, which grows proportional to the number of cores on the chip, you know, unless we grow the cache per core. That pressure on memory bandwidth is leading to the integration of DRAM with the processor die through technology, silicon on silicon technologies like HBM, high bandwidth memory. Now this helps, but it also runs into a problem when the cost per transistor no longer goes down. And then again, you have to look for more efficient means of increasing performance. Perhaps the biggest challenge to multi-core, however, is not cost, but power. So, you know, we are reaching a point where even though we grow the number of transistors, we can't really bring the power per transistor down at the rate we need to. And if this is the case, then when you double the number of transistors, ultimately your power also goes up by a factor of 2. Now we're not quite there yet. You know, technologies like FinFET and Gate-All-Around do help, but definitely the power per transistor is not coming down at the rates that we need to. And one way you can see this is that again, for server processors, the processor power has grown substantially. You know, for commodity servers, it's not that long ago that we might have had a CPU power just over 100 watts or so, and you know, the latest announced processors have power in excess of 300 watts. So when you continue to get more transistors, but you don't, the power per transistor switch doesn't go down, then you end up in a situation that has been referred to as dark silicon. You have more transistors available than you can switch. So that is, you know, a place where multi-core also runs out of gas, because if I instantiate twice as many cores, but I can only turn half of them on, obviously I'm no longer getting ahead. So as we reach a point where multi-core is no longer an efficient enough mechanism to improve performance, we will have to turn to specialization. So with specialization, we can make use of the additional transistors to provide improved performance for particular types of functions. And because we can no longer afford to turn all the transistors on, it is actually an effective use of the transistors that are available to us. Now, specialization is not new. I mean, it has been used to improve processor performance for a long time, going back to floating point unit and vector units, etc. More recently, things like AI processors and network processor security engines, etc. The ultimate in special purpose design is an ASIC, an application-specific integrated circuit. However, designing ASICs is difficult as an economic activity when general purpose computing still improves. You know, if a microprocessor, if it takes me 10 years to recoup the investment on a very specialized design, then if general purpose processing still goes through multiple iterations of improvement, chances are that even though I may have started out at an advantage with my specialized design, after a few years, general purpose processors would catch up, and therefore I would not have an advantage for a long enough period to recoup my investment that I had to make in my more specialized design. Whereas ultimately, when technology really saturates, of course, the general purpose processor would not catch up, and I would have the time that I need to recoup the investment in my more specialized design. Reconfigurable logic, or FPGAs, are interesting in that they strike a balance between designing something for just a single purpose and efficiency. You know, an FPGA is less efficient than a special purpose design, but much more broadly applicable and requires a much lower level of investment. A key challenge with FPGAs is to make them easy to develop for and use. And we will get to this in the second module where I will introduce OpenCAPI, how OpenCAPI and similar interfaces can help make FPGAs easier to program and integrate. This chart summarizes our motivation to look at accelerators from a technology perspective. The exponential growth of single-threaded processors came to an end with the end of Dennard scaling. Multi-core processors will not improve at an exponential rate once power limit and transistor cost limits bring an end to the exponential improvement there. Specialization, introducing hybrid or heterogeneous designs are a next way to still improve the efficiency, both power and cost efficiency of our designs. And ultimately, we will turn to very specialized designs in the form of ASICs and combine multiple ASICs, perhaps as chiplets, into computers for particular purposes. FPGAs, or reconfigurable logic, is a good intermediate solution that allows us to explore the specialization space without having to make very large investments that are difficult to recoup. In the first half of Module 1, we discussed technological and microarchitectural means of improving computer performance. We discussed concurrency and specialization as two fundamental ways to improve performance and efficiency. And we explained how it is increasingly difficult to improve the performance of general purpose CPUs because of technology and current concurrency scaling limits. And accelerators, because they are intrinsically more efficient, or can be, provide us a next horizon for improving the performance of our computer designs.